Now, in this example, we are given not a single, but two iterated integrals written with respect to x first. Now, we want to change the order, and we know that to change the order in an iterated integral, we have to express it as a double integral, and then look at the domain D and write it with respect to the other variable. So let us start with the first one. Well, in the first one, of course, the critical part is x is equal to 1 minus root y. Well, this is nothing but y is x minus 1 squared. Okay. But when taking the root, we have taken the negative root. In other words, x is smaller than 1. Well, this parabola is something like this. It's a shifted parabola to x equal to 1. And the fact that x is less than 1 says that we are talking about the left branch of the parabola. Okay. And we start from, that is, x starts from 0. We look in the x direction. It moves from x equal to 0, the y-axis, up to the left branch of the parabola. In the meantime, y goes from 0 to 1. Well, 1 is clearly this point. When x is 0, y is 1. So this is our view. Similarly, for the second one, again, 1 plus root y is the key in this discussion. Okay. This is, again, the parabola y is x minus 1 squared. But when solving for x, we have taken the positive root, and so it is the right branch. When we solve it. Now, x starts again. We are looking in the x direction. From 0, that's the y-axis, goes up to the right branch. Okay. In the meantime, y changed from 0 to 1. Well, 1 is here, and it is also somewhere here. Okay. At 2 or 0, y is 1. So we end up with the following region. This is our D2. So the wanted expression becomes, okay, the first one is a double integral over D1. But we have a minus sign, so it is negative of integral over D1 plus the other one is precisely integral over D2. Okay. Now, if we say that this region is D, then by looking at the previous pictures, we see that D2 is the union of D1 and D. So integral over d2 is integral over d plus integral over d. Now, this tells us that I, which is the negative integral over d1 plus the positive one over d2, is nothing but integral over d. Well, knowing what d is, we can now write I simply with respect to y first. Okay. Because D is a simple region with respect to y first. That is, if you look upwards, you have a first curve, the parabola, and then a last curve, a horizontal line, and x changes 0 to 2. So it starts from the parabola at the bottom. Y is, okay, x minus 1 squared up to y equal to 1, and x from 0 to 2. Okay. Right, so this simplified the expression considerably. Okay. Well, you can calculate this now much more easily. In the next set of examples, we want to find some volumes. Okay. So find the volumes of the solids. Well, a solid always refers to a certain part of space which contains its inside as well. So it has a volume. Okay. Volume is just a number, but solid is a three-dimensional subset. Okay. Of the solids bounded, or let me just say, right, bounded by, okay, the surfaces given. Okay, let us start with our first example. Okay, they are bounded by the surfaces. Y is x squared, y is 1, z is minus 1, and z is 2. Okay. Now, in such problems, it's always advisable to feel the geometry. So make a rough sketch, okay, as best as you can. First of all, we observe that y is x squared and y is 1 are cylinders. That is, you don't have z in them. Okay? So they are, one is a plane, the other one is a okay, vertical going parabola. So they bound, okay, actually our base D. So if we sketch them, we easily see that we have, okay, y is x squared. So we have, okay, such a parabola, and y is 1. So it is bounded by y equal to 1. These two curves move up and down. Okay, because there's no z. For every z, we have the same figure. So it goes infinitely up and down. But horizontally, it's bounded by minus 1 for z, a horizontal plane, and z equal to 2. So the figure then looks like something like this. Okay, it can go up and down. Okay, we have the same picture here. And we have the same picture down here. Okay. So this is the solid in question, where this level is a horizontal plane, z is 2, and the bottom level is a horizontal plane, z is 1. So this says that, indeed, if we call, okay, this region, the base region, RD, then the volume, okay, is integral over D of the difference between two surfaces. Okay. These surfaces are 2 and minus 1. One is z equal to 2 from the top. The other one is z is minus 1 from the bottom. So it happens that we are integrating 3 over d, but d, as in the previous example, is a region which is simple with respect to y or x first. So say we use y first. When we look in the y direction, this is 1, and this is x squared. So y starts from x squared, goes up to 1. And in the meantime, x runs from minus 1 to 1. So this is the volume in question. Okay. This was a pretty straightforward example. Okay. Well, actually, one can easily calculate that. That happens to be 4. Okay. So, well, the second one is, that is x squared plus y squared. This is one of the surfaces which bounds our solid, and above unit square. Okay. Well, by unit square, we mean the d, which is 1 in the x squared. Well, this is again pretty straightforward, because when we look at, okay, the solid, which is bounded by the paraboloid at the top, so the solid lies below the paraboloid, because this is the top surface. The bottom surface is situated in the xy plane. Okay. So it looks like perhaps something like this. Okay. And we have our paraboloid here. So the sides, okay, go like this. Okay. Okay, well, actually, wait a minute, what did I do over there? That should be the paraboloid, so it would go, no, that's not a good picture. So that would move from here on up to this point, up to this point, and finally up to this point. Okay, so something like this. Okay. So this would be the solid whose volume we are calculating. At the top, we have the paraboloid, At the bottom, we have the unit square. Well, so the volume is, because the paraboloid is non-negative all the time, yeah, we can even write our iterated integral directly over the square. It would be 0 to 1. So again, this would be a pretty straightforward example. Now the next one is a little bit, okay, more interesting. That is y minus x squared. Y is 1, and z is 0. Now to understand what this really looks like, we see that these are planes, so they are easy to deal with. But first, we have to sketch what this is. Okay. This would tell us, actually we sketched that before, it tells us that this is, if z's are constant, that is, if we look at the intersections with a horizontal z equal to constant plane, we will get curves which are parabolas, but with a shift of z. So we did, as I said, this before. Okay, for example, when z is 0, okay, these are x and y's, then we have y is x squared here directly. But if we go up a little bit, okay, then z is positive. So this is the parabola shifted upwards. So it is somewhere here. And if we go below, okay, it will be a parabola shifted downwards in the y-axis. So this would be something like this. So let me use some color here. This would be a straight line. We figured that out last time, so I'm not repeating. And it is such a shape. Now what do we do with this tilted shape? Okay, let me draw it in a better way. Okay, it looks like this. It's something like this, a tilted, curved surface. Now we cut it with z equal to 1, z equal to 0. That means we have some bottom part which bounds it from below. And we have y equal to 1 curve. Well, y equal to 1 curve is a vertical curve, plane, sorry. It's a vertical plane, okay, which is parallel to the zx plane here. So it comes vertically, okay, and when you cut it with a vertical plane, perhaps something like this, okay, you would be obtaining as an intersection something like this. When you cut it in a vertical way, it will hit somewhere here, and it would be something like this. Okay. It's in this vertical plane. Now, using your imagination, you can now see our bounded solid. Okay. Basically, it's bounded by this curved surface. From the top, you have a vertical surface cutting, and from the bottom, you have a base Okay. Well, a better picture could be perhaps something like this. This would be let's put something like that, and this. Cutting it vertically, exactly, you get this. Okay. So the defining curves are these. Now, the important thing to observe here, okay, is that from the top, okay, we have precisely this surface bounding it. Okay. And at the bottom, we have this D, the base, which is determined by y is 1 and the bottom z equal to 0 plane. Okay. And of course, this curve is the intersection of our surface with z equal to 0. Well, all in all, this means that base, that is our D in the xy system, okay, is a parabola. That is, it is the parabola z is okay, x squared minus y, but z is 0, so it is just y is x squared. And we have the vertical plane, y is 1, giving us this D. So the volume in question is the integral over D of the positive surface, y minus x squared dA, which can be written over this D as an iterated integral. Well, say we have y first, so y changed from x squared to 1 and x minus 1 to 1. So after calculating this, we end up with the volume in question. Okay. Well, right, my next example is bounded by z is 2, z is y, and y is x squared. Okay. Noting that these are actually surfaces in space, okay, we observe what's happening here. Well, you can leave one out and see what's happening directly. Here, the only non-plane is y is x squared. It's a cylinder which goes vertically up. So it looks like the following. Okay, let me put them in coordinate system. Okay. Well, y is x squared. And it goes up and down. Okay. So maybe I should show it like this. And it goes down as well. This is the level, z is 0. Okay. Now, we bound this with z equal to 2 from the top. Okay. So you note that you have something as follows. Now we have, okay, such a figure, okay, a vertical one, and okay, we have a bound from the top. Now, to describe the whole solid, okay, we need a plane which cuts it in a slanted way, so that it's bounded from above, and if we cut it like this, this will give us precisely a well-defined solid. So, okay, if we cut it like this, okay, that means, of course, in the plane ZY, we have a line, okay, and we extend it along the x-axis. But this is precisely what z equal to y is. It extends along the x-axis, okay. So in the ZY plane, okay, in this plane, we have a curve and we move it along the x-axis. It cuts this exactly in a slanted way. So at the end, okay, we get something like this. We have the z-axis. At the top, we have our z equal to 2 plane, okay, and we cut it in this way with the plane z equal to 1. Of course, when it cuts into this curved surface, you don't get straight lines here. You get something like a parabola. So the whole picture then looks like this. Now, having identified the picture, the rest is easy. Obviously, the volume in question is the double integral over d. Okay, whatever d is, we will find it in a minute. And it is bounded from below. Okay, we are looking in the z direction. So the lower surface is the plane z equal to y, because it cuts it this way. The top plane is z equal to 2. Okay, so it starts from z equal to y. Okay, that's the lower one. We subtract it from the top one, and then we have dA. Now, this is a solid bounded between two surfaces. The lower surface is z equal to y. The top surface is z equal to 2. Okay. But what does it rest upon? What's the base? Well, the base is in the xy plane, and it's a projection when you look from the top. So the projection onto the xy plane is from the picture, okay, precisely the projection of this horizontal region. And that is determined by, okay, the intersection of z equal to y and z equal to 2, so it is y equal to 2. So we have the following. First of all, it's a parabola. Y equal to 2, y is x squared. And the line segment we see there is the intersection of z equal to y with z equal to 2. So y is equal to 2. So this is, okay, let me say, the intersection of z equal to 2 and z equal to 1. So it is y equal to 2. Well, this being our b, the rest now is easy. So volume is the iterated integral 2 minus y, say dy dx. Looking in the y direction, we have x squared to 2, and of course x changed from minus root 2 up to root 2. So this tells us that indeed this gives us the volume in question. Now, as a last, not example, but remark, let me say, we also have a similarity or a generalization to the one-dimensional case. I will shortly mention that. Okay. A mean value theory. For double integral. Now, to understand what we are talking about, let us recall the mean value theorem for integrals, meaning definite integrals. Okay, it was the following. Okay. Let f be continuous on AB. Okay. Then there exists an x0 in AB such that we have f of x0 is equal to the integral divided by b minus. Okay. This was the standard mean value theorem for integrals. Actually, this was also called average value. Okay, we saw it before when we discussed the integral. Now, how can we generalize this to functions of two variables? Well, it's more or less similar, as you can observe, okay? Namely, a suggested generalization namely, let f be continuous on D. It's a subset of R2. Okay. Then there exists a point in D such that f of P0 is, I'm copying from here, just cheating. Okay. It's the integral of f divided by, well, definite integral became double integral, and b minus a, well, actually b minus a is, well, a difference of two numbers, but it is the length of the interval. So here we could expect the area of D. Now, this is a logical generalization, of course, but there are problems because we are not so sure here which properties of the interval we use. Now, generalizing the interval and retaining, keeping its properties, okay, is not that obvious. So what's the nice generalization? Well, what do we know about a closed interval? Well, certainly it's closed. And it doesn't go to infinities, it's bounded. So closedness and boundedness are important. Okay. But there's another property of the interval, which we take for granted. But in two variables, it becomes series. Okay. So, since the interval is closed and bounded, okay, logically, we should expect that B is closed and bounded. We already had these definitions or explanations about these terms. But is that all? Okay. Namely, are these the only properties of AB that we use? Now, to explain this, let me give an example. Okay. The example is, let me see. Yes, here. Let us apply this mean value theorem for one variable. Okay, to a closed and bounded set. Okay. Namely, okay, we will consider the following. The integral of x to be simple. Okay, I will not write a to b because I will not evaluate it on an interval. I will evaluate it over an interval 0, 1, union 3, 4. Well, you may ask, well, we didn't define such things, but these are disjoint intervals, so you can readily assume that it means 0 to 1 plus 3 to 4 x dx. Okay. Well, one can calculate these things, and when one does, one obtains 4. Okay. Well, remember we divided this by the length. Now, the length of an interval is clear, but if you have two disjoint intervals, it is more or less again obvious. You can take this length as, okay, 1 minus 0 plus 4 minus 3, which is 2. Okay. So the integral is, okay, 4. The length is 2, so divide by 2. So the question is, find, okay, f of x, where x is in 0, 1, union 3, 4, such that, okay, f of x is equal to 2, which happens to be the integral divided by the length. But f of x is x. And, okay, there is no 2 in this set. So this does not exist. Such an x does not exist. Which means that, okay, if we want to apply the mean value theorem in one variable, it fails. Okay. What's the reason here? Well, this set is still closed and bounded, as an interval was, but it does not have a property which the interval has. That is, okay, in the interval, okay, if we choose any 2 points, everything in between is inside the interval. Here we don't have it. These are in 2 pieces. This set is in 2 pieces instead of 1 and 2. So this is a fundamental property that we use when we discuss the mean value theorem. It is already there in an interval, so we didn't pay much attention to it. But in the case of 2 variables, this becomes important. Okay. Now, okay, all points between any 2 points in an interval lie in the interval. Now, this is a very important property. You can also regard it as, if you have 2 points in an interval, you can connect it with a curve. Well, the curve is the interval in question. Okay. Now, a generalization is the following. Okay. A set D in R2 is called connected. Actually, arc-wisely connected, but we will not work on it. Okay, it's called connected if any 2 points in D can be connected by a curve lying in D. Now, this is a property satisfied by the interval automatically in R. In our counterexample, this was not true. Okay. Namely, if you took the point 0 and a point 3, you cannot connect it with a curve which is inside this union. So, let us see very rough examples. For example, okay, a unit disk is connected, because if you choose any 2 points, you have a curve connecting them, and the curve is inside. Okay. Or, for example, a star-shaped, okay, region is connected, because any 2 points can be joined by a curve inside the set. But of course, this is not connected. Or, more seriously, a set without boundary and another circle tangent to it, but both without boundary. Okay. These are not connected. Because you cannot connect a point here to here without jumping across this line, which is not inside. So these are not connected. So this connectedness issue is important. Okay, let me state the theorem. Okay, let F be continuous on D, which is closed, bounded, okay, and connected. Then there exists a point in D such that f of P0 is indeed the integral divided by the area. Okay. As before, we will call this value the average value. Okay. So the calculation is obvious. I will just show this in an example, something like an application. Okay, the average value, okay, of x respectively y, okay, are called, okay, components of the centroid. Okay, which means actually this is the definition of the centroid, so I will not be very rigorous, but as a common sense, it means the center of mass. From physics, you have heard this a lot of times. Okay, with density 1. So these are mathematical identities because density is 1. You are not dependent on the matter in question. Okay, so okay, x bar, which is the average value with respect to x. So it is dx dA divided by area of B, and y bar, which is dy dA divided by area of B, okay, give the centroid. Okay. This is the definition. Let me apply this to an example. By the way, a center of mass or centroid means the following. If one hangs, okay, a region, okay, something like this. This is the region R. Okay. If you hang it like this, okay, under gravity, it will rotate to the position, okay, something perhaps like this. like that, where this is the point x bar, y bar. Okay. Until the rope passes through the centroid. Rope is aligned to the centroid. Okay. So this will rotate. This is independent of the point in question. Namely, whichever point this is always what will happen. So this is the physical meaning of a centroid. So the example is the following. Find the centroid of the upper half disk. That is this. This is D. Okay. Well, this is a simple calculation. Namely, we have to find x bar. That's the double integral over D of x dA over area of D. Okay. The integral is, of course, an iterated integral. You have x, say, dy dx, y from 0 to the root of r squared minus x squared, and x from minus r to r. The area, of course, is pi r squared over 2. Okay. Now, because it's with respect to y, you can easily calculate this. It is minus r to r, x root r squared minus x squared dx. But of course, this is an odd function from minus r to r, so it is 0. Okay, this is something we expect because of symmetry of both sides. Now for y, okay, we have double integral of y divided by area of D. And of course, double integral dy is integral of y, say, dy dx again, from 0 to root of r squared minus x squared, and from minus r to r. Okay. Well, this, of course, is 1/2 of y squared, which simply means r squared minus x squared dx minus r to r. And you can calculate this. That would be 1/2 of, well, r squared x minus x cubed over 3 from minus r to r. Actually, it's an even function, so you can take 0 to r and multiply by 2. So it's 1/2 times 2, 0 to r. So it's r cubed minus r cubed over 3, which gives you 2/3 of r cubed. Okay. Now, so y becomes 2/3 of r cubed divided by pi r squared over 2. Okay, so it is yes, 4/3 pi of r. Well, you can observe that this is a number, okay, less than 1/2 as expected, because in a circle, this is r over 2, but y bar is below it. Okay. This is expected because the mass of the circle lies below the half. So the centroid is 0 and 4r over 3 pi. Çok mu oldu gene?